Hello everyone, my name is Elijah Proctor, and today we're going to talk about exploratory data analysis and Python, and we're going to handle 6 tasks for this project. And so first we're going to talk about, based on our assigned reading, how to approach EDA in a professional manner. So first step is to summarize the data set so that we can understand key characteristics such as the mean, the median, and distribution of important variables. An example of that is summarizing the distribution of credit limits among customers. This can be helpful in providing an initial insight into their average bill amounts. After we do this, we can use visualizations that can play a crucial role in exploring patterns in the data. We can use tools like correlation heat maps that can show how variables like payment history and credit limit relate to default behavior. Our bar charts can be used to illustrate default proportions based on demographic factors that include age, gender, or marital status, and this gives us a clear picture of data trends. Finally, we can use a correlation analysis to help reveal relationships between variables, such as connections between default status and credit limit or payment history. This analysis highlights the most significant factors influencing defaults and gives guiding further investigation. And so in order to perform this EDA, we're going to use a data set called the default of credit card clients dataset. And so this contains information on default payments, demographic factors, credit data, history of payment, and bill statements of credit card clients in Taiwan from April of 2005 to September of 2005. And so this data has 30,000 rows and 25 variables. So it is ideal for EDA. It is relevant for finance, risk management, and consumer behavior applications because of its real-world credit card data. And by analyzing this data set, we can gain valuable insights such as default rates among different age groups or education levels, and this can guide credit policies and financial decisions. And so this code is very simple. We're just loading the data set and then just printing out the first 5 rows so we can get a glimpse of what data is presented to us. Our third question is conducting our EDA. So let's just go over this summary of the code. So here we're performing an EDA. We begin by loading the data set and we make sure that there's no missing values so that we maintain data quality. Any type of categorical variables such as our sex, education, and marriage are replaced with easily understandable labels so that the data is easier to interpret. We generate a summary statistics to give us an insight into numeric variables, and it gives us a look at the average values, variation, and overall distribution of the data. We analyze the distribution of demographic factors like gender, education, and marital status, and so that we can understand the data set structure. We use a correlation heat map to visually display relationships between our numeric variables and default behavior. Our bar charts and histograms are used to show default rates by education level and the distribution of credit limits. And these visualizations and analyses together give us a deeper understanding of the data set and shows patterns or trends that address research questions related to credit limit, demographics, payment history, and default behavior. And so that kind of covers what this script is doing here. So let's go over our results. First, let's talk about the summary statistics. And so this data set, as I said before, has 30,000 entries with a bunch of numerical and categorical variables. And so our key statistics such as our mean, standard deviation, and distribution for variables like our credit limit and our credit limit and our bill amounts, they give us an overview of the data. And so, for example, the average credit limit is about 167,000. with a large standard deviation, which means that, well, it basically indicates a wide range of credit limits. Let's go over our categorical variable distribution. So the dataset's demographic breakdown shows that there are more females than male clients. Education-wise, most clients have a university or graduate school background, and a significant portion is single, followed by married individuals. Here is our correlation heat map that reveals relationships between the variables. There is a strong correlation between the billing amounts 1 through 6, and this indicates that higher bill amounts across months are correlated, and which is the same for the payments as well. So payments 1 through 6 also has a high correlation. Our default rate by education bar chart shows that individuals with university and graduate school education have the highest default rates, whereas fewer defaults are observed among clients with high school education or lower. Our credit limit distribution, histogram for credit limit distribution. This shows that the majority of customers have credit limits below 200,000, with a sharp decline in frequency as the credit limit increases. Only a small proportion have limits that are over 500,000. Now for question 4, talking about research questions and using statistical techniques to measure the strength and direction of the relationship. So we have 6 questions that we hope to answer. What are the factors that are linked to credit card default? What is the relationship between credit limit and probability of default? What is the impact of demographic variables on the likelihood of default? Is there a correlation between default and payment delay? What is the distribution of credit limits and payment quantities among various demographic groups? And what is the impact of the balance of invoices on the probability of default? And so what we're doing here, it'd probably just be easier to go over the code. First, we're basically performing an exploratory data analysis and statistical evaluation on our credit card data set. And so first we have to load the data set, and then we're going to map categorical columns like the sex and education and marriage to a human readable label for better interpretation. Then we perform a summary statistics of the data set and then display to understand the key numeric characteristics such as the mean, median, and distribution of values. And to visualize relationships within the data set, we use a correlation heat map to see how different numeric values are related. Our bar chart is used to compare default rates across education levels, and then our distribution of credit limits is shown using a histogram, helping observe the range and frequency of our credit limits. And so these are the same visualizations that we had in question 3. But what is different here is we have a logistic regression model, and this is used to predict the likelihood of credit defaults using factors such as the credit limit, the age, and the payment history. The performance of the model, we evaluate it using metrics like precision and recall. And finally, we use a chi-square test to examine the relationship between education level and default behavior. And this gives us insights into whether certain groups are more prone to defaulting. Let's go over our results. So these are the same results as question 3, so I'll gloss over these. What I wanted to get over was this part. And so we have our classification report from the logistic regression model that shows that the model's accuracy is about 81%, and the precision for non-defaulting customers is high at 82%. And this means the model correctly identified most non-defaulting customers. However, though, the recall for defaulting customers is lower, which is 23%, and this indicates that the model struggles to correctly identify all defaulting customers. Our chi-square test results with the statistic of 163.21 and a very low p-value suggests a significant relationship between education level and default behavior. Now for our final task, or for our fifth task, here we're going to fit a regression model to investigate the relationship between two or more variables in the data set. Let's go over this little report that we had created. So we're in this EDA, we have a linear regression model to explore the relationship between three variables. We have our age, our credit limit, and our payment, our recent payment status. And so the target variable is the billing amount, which is the amount billed in the first month. And so after splitting the data into training and testing sets, we have a model that was trained and assessed for its predictive accuracy. And we performed various checks to ensure that the assumption of regression were met. We have a linearity check tested by plotting predicted versus actual values, where random dispersion around a diagonal line would confirm the assumption. Our residual normality was checked using a histogram and a QQ plot. Homoscedasticity was verified by plotting residuals against fitted values, ensuring constant variance without patterns. And so our model's performance was measured using R-squared value and mean squared error. And if we have a higher R-squared value, this means that we have a strong model fit. And this helps us to understand how our predictive variables influence the billing amounts on our credit cards. So let's just go over our results here. And so in our linear regression analysis, to predict the billing amount in the first month based on our age, credit limit, and payment status. First, we have the categorical columns were mapped successfully, which is good. And then the data was split into a training sets, and regression model was trained. So we have our mean squared error, which is very large. It's like, I think that's 4 billion. 4.7 billion, which means that the model's predictions are far from the actual values. Our R-squared is 0.151, which means that only about 15% of the variance in the billing can be explained by the model, and this suggests that the model is not really a good fit for the data. Our linearity check here, there shows that there's has a tight grouping around the diagonal line, which would indicate a better fit. Our plot indicates some relationships, but not super strong. Our normality check here with the residual plot shows that there's approximately it's approximately normally distributed, but there is some spread. The QQ plot also highlights deviations from normality, particularly at the extremes, and this means that the residuals do not perfectly follow a normal distribution. And lastly, our residuals versus fitted values plot shows a fan-shaped pattern, and this indicates heteroscedasticity, or non-constant variance, which violates one of the assumptions of linear regression. And so this means that the model's performance varies across different fitted values, leading to unreliable predictions for some portions of the data. So with all of that, let's talk about the process of analysis and our results from our EDA. And so let's kind of zoom out a little bit. So in this analysis, we examined a credit card data set and tried to explore the relationships between various factors such as our age, credit limit, and our payment history, and evaluate their impact on billing amounts and credit card default behavior. We first cleaned the data and converted our categorical variables like our gender and education into understandable labels. Then we use visualizations like our correlation heat map, bar charts, to highlight important trends such as the relationship between payment delays and default rates. We also built out a linear regression model to predict billing amounts based on age, credit limit, and payment history. But our model had a low accuracy, which means that it did not explain the data well. Additionally, we checked the assumptions of the model and we found some issues like uneven prediction errors. So overall, while we found useful insights about the data, improving the model could would probably lead to better predictions in the future. So that is our EDA, our exploratory data analysis. Thank you for listening. That is all.